Dear student, I am Dr. Harold Thomas, Professor in Applied Geology, Dr. Hari Singh Gaur Vishwavidyalaya Sagar. Today, in this course, I will deliver my lecture on regional metamorphism of Pelitic rocks. I will cover this topic in 4 parts. In part 1, I will proceed under the following heads: regional metamorphism, introduction, Barrovian phases series, geolite phases and mineral assemblages. Hope it will be useful for you. Try to be regular in course. When pre-existing rocks are subjected to high temperature and pressure, metamorphism known as regional metamorphism. In regional metamorphism, both temperature and pressure increase due to several mechanical reasons. For example, high heat introduction or perturbation of geotherm associated with increase of pressure as a result of structure duplication. In converging plate margin, regional metamorphism occupy the thousands of square kilometer area commonly in Precambrian silt. Regional metamorphism develop in orogenic belts where lithospheric plates converged. The regional metamorphic rocks are typically foliated and occur as schist, amphibolite, gneisses, migmatites and gaullites. Foliation in the result of deformation which is almost synchronized with metamorphism as documented by rotated garnet during growth and wrapped by schistosity. Thus, regional metamorphism is characterized by large area of prograde mineral assemblages with chlorite, biotite, garnet, stolite, kyanite and sillimanite in pelitic composition. On the basis of pressure and temperature, we can divide the metamorphic phases into 3 types, mainly A. Phases of low pressure, second, phases of intermediate pressure and third, phases of high pressure. Mayasero originally recognized 3 different phases series: 1. A geolite, prehenite, pumpelite, blue schist, eclogite type; second, a typical Barrovian type characterized by green schist, epidote amphibolite, amphibolite and gaulite type characterized by paragenesis of kyanite sillimanite type; and third, an Abukama type of green schist, amphibolite, gaulite characterized by the paragenesis of andalusite sillimanite type. Phi et al. In 1958 divide the metamorphic phases into 2 types on the basis of pressure, that is contact metamorphism where pressure is less than 4 kilobar and regional metamorphism where pressure is more than 4 kilobar. Regional or Barrovian metamorphism covers large area of continental crust typically associated with mountain range, particularly subduction zone or the roots of previously eroded mountains. The regionally metamorphosed rocks occupy during an orogenic events the collision of 2 intermediate pressure or Barrovian type are listed in order of increasing temperature and pressure of metamorphism. First, geolite phases; second, green schist phases; third, amphibolite phases; and fourth, gaulite phases. The Barrovian phases series occupy in a number of Paleozoic mountain belts as well as in some of the Precambrian age. The classic region in the Scottish Highland. Other belts with Barrovian rocks occur in Colorado, British Columbia, Alaska, Venezuela, Spain, Southern Europe, Asia and Japan. Precambrian belts of Barrovian rocks occur in the Black Hill of South Dakota, the Rocky Mountains, Labrador, Ontario, Canada, and Singhbhum in India. The Paleozoic orogenic belts are clearly associated with convergent plate margins. Both Barrovian and Buchan facies series developed at such margins in convergent zones. Regional heating due to the rise of plutons into the overlying plates. The plate above the subduction zone is the general cause of metamorphism. Migrating fluids may also transport heat. The zone of metamorphism in the Scottish Highland, originally described by Barrow in 1893, includes 6 distinct index minerals: chlorite zone, biotite zone, almandine garnet zone, stolite zone, kyanite zone, and sillimanite zone. The lowest grade is the zeolite facies, which forms under condition just above those of the diagenesis assemblages, is characterized by the clay minerals assemblages, may include kaolinite, illite, chlorite, quartz, analcite, etc. At slightly higher grade condition, assemblages of the zeolite facies are replaced by those of the prehenite, pumpelite facies. As the PT condition increase, greenschist facies assemblages with new minerals from typical assemblages in peltic rocks includes white mica, that is phengite, chlorite, chloritite, quartz, albite, magnetite, biotite, epidote, garnet, pyrophyllite, kyanite in almandine zone of greenschist facies. The greenschist facies, amphibolite facies boundary is a broad zone. The disappearance of albite marks the maximum upper limit of the greenschist facies. Thus, albite, like pyrophyllite, is absent from amphibolite facies rocks. Stolite rather than chloritoid occur in lower part of the amphibolite facies, and the aluminous silicates, kyanite, at lower grade and sillimanite at higher grades characterize aluminous bulk composition. Typical assemblages includes white mica, chlorite, biotite, quartz, plagioclase, garnet, magnetite, stolite, ilmenite, kyanite, sillimanite. The gaulite facies is distinguished by the general absence of white mica and the presence of orthopyroxene and plus minus cordierite. Peltic assemblages include biotite, garnet, sillimanite, potash feldspar, andesine, quartz, plus minus cordierite, orthopyroxene, sillimanite, zircon, etc. The quartzo-feldspathic rocks differ from the peltic rocks. Quartz and feldspar are the dominant phases rather than the phyllosilicates, and calcium-bearing phases are common. Additional minerals that may occur include stabilite, calcite, stapylomelain, actinolite, and hornblende. Characteristics of peltic rocks. First, pelites, Greek words is a peleos, means clay, is a descriptive name for a clastic rocks with a grain size of less than 1/16 mm, originally sands or silt size. Examples include slate and mudstones. Second, peltic sediments are very fine grained, commonly more than 2 mm. Mature clastic sediments derived from weathering and or erosion of continental crust. Third, the mineralogy of peltic sediments is dominated by the fine alumina, potash rich phyllosilicates such as clay, montmorillonite, kaolinite, fine white micas, cerussite, paragonite or phenzite, and chlorite, all of which may occur as detrital or orthogenic grains. Fourth, other common constituents include feldspar, albite and potash feldspar, iron oxides and hydroxides, zeolite, carbonates, sulfides, and organic matters. Fifth, during diagenesis, various change of the clay minerals take place in response to circulating fluids and with increasing temperature. Montmorillonite and clay minerals, mainly illites, are decomposed and produce muscovite and chlorite. Therefore, peltic rocks are argillaceous sediments contain kaolinite, fensite, chloritoid, and quartz as clastic fragments. All are responsible for the starting mineralogy for the Pelitic rocks. 6. The chemical characteristics that distinguish Pelitics from other common rocks are high Al2O3, K2O, and low CaO. 7. The high proportion of mica in metapelites result in the common development of foliated rocks such as slate, phyllite, schist, and gneisses. Increasing pressure and temperature condition, slate give rise to give rise to slate, give rise to phyllite, schist, gneiss, megmatites, gaullites. Low, medium, and high grade metamorphism. The index mineral which define a zone does not commonly display when entering the next higher grade zone. For example, the first appearance of biotite is at the biotite isograde, where chlorite is seen to the reacting to produce biotite. Biotite does not disappear at the garnet isograde, and we can continue seen through the garnet, stellite, kyanite, and sillimanite zone. Stellite, kyanite, and sillimanite only occur in the stellite, kyanite, and sillimanite zone respectively. The texture or structure of the rocks change from slate, phyllite, schist, gneiss, megmatites, and finally gaullites. Slate and phyllite in the chloride zone to different types of schist in the biotite, garnet, stellite, and kyanite zones, and normally gneiss in the sillimanite zone. The composition of the plagioclase change from increasing grade of metamorphism. It is nearly pure albite in the chlorite and biotite zone and becomes somewhat more calcic oligoclase and andesine in higher grade zones. During Barrovian type of metamorphism, where pressure in the medium grade of metamorphism are higher than of the aluminous silicate stipple point, the resulting aluminous silicate mineral sequence is kaolinite, pyrophyllite, kyanite, sillimanite, which we can observe in AKF and AFM diagrams for the Pelitic rocks. The presence of either kyanite or andalusite on metamorphosed cells and slate stone at the medium grade of metamorphism is one feature that distinguishes the regional or Barrovian type with contact or bouquet type facies series. With the individual detailed study of different facies formed during regional or Barrovian type of metamorphism, that is from geolite, greenschist, amphibolite, and gaulite facies metamorphism, we understand that rock of similar bulk composition, different mineral assemblages in response to different set of pressure, temperature condition, or rocks with different in bulk composition will develop different minerals assemblages in response to same pressure, temperature condition. If we compare all the facies during regional or Barrovian type metamorphism, the different zones were based on the first appearance of a particular mineral called an index mineral, which is characteristic of the zones. These boundaries were later called isograde, equal grade, and likely present surfaces in a three-dimensional sense. Chlorite zone, slate and phyllite, quartz, chlorite, muscovite, albite. Biotite zone, phyllite and schist, biotite begins to replace chlorite, quartz, muscovite, albite. Almandine zone, schist, quartz, muscovite, biotite, almandine, albite. Stellite zone, schist, quartz, biotite, muscovite, almandine, stellite, oligoclase, etc. Kyanite zone, schist, quartz, biotite, muscovite, oligoclase, almandine, kyanite. Sillimanite, gneiss, quartz, biotite, muscovite, oligoclase, almandine, sillimanite. For detailed understanding of the regional or progressive metamorphism of peltic rocks, we have to take the help of certain diagrams like ACF for geolite facies, AFM diagrams for greenschist amphibolite facies, and A-F-, M- diagrams for gammalite facies. We have to concentrate on the peltic assemblages, and on the basis of diagram we can find out the important assemblages and related reaction to explain the regional metamorphism of peltic rocks. The characteristic minerals of geolite facies are lawsonite, lomentite, prehenite, pumpelite, quartz. No chemical reaction take place. Figure 1. Sedimentary environment, temperature less than 200 degrees centigrade. Characteristic minerals of geolite facies, important reactions. Disappearance of clay minerals and analcine. Analcine plus quartz give rise to albite plus water. Another reaction is hollandite give rise to lawsonite, lomentite, quartz plus water. Lawsonite plus lomentite plus quartz give rise to pyrophyllite plus epidote plus water. Montmorillonite, pyrophyllite, epidote plus chlorite plus water. Kaolinite plus quartz give rise to pyrophyllite plus water. The disappearance of lawsonite, lomentite, prehenite, pumpelite, montmorillonite and kaolinite marks the upper limit of geolite facies and also the lower limit of greenschist facies. The kaolinite plus quartz give rise to pyrophyllite plus water. Reaction number 1 occur at 375 degrees centigrade 4 kilobar and 415 degrees centigrade 6 kilobar. This mark the beginning of chloride zone. Chloritoid appear in the rock rich in aluminous and FeO and poor in alkalis. The chloritoid formed by the reaction kaolinite plus Fe chlorite give rise to chloritoid plus quartz plus water. I will cover this topic under the following heads: chloride zone, biotite zone and almandine garnet zone. Hope it will be useful for you. Try to be regular in course. The greenschist facies include the common products of low-grade, regional and dislocation metamorphism. The beginning of greenschist facies is characterized by the following reactions: kaolinite plus quartz give rise to pyrophyllite. Reaction 1. This reaction was carried out by Thomson in 1970 at 325 degrees centigrade 1 kilobar, 345 degrees centigrade 2 kilobar, 375 degrees centigrade 4 kilobar. Characteristic minerals. Greenschist facies are characterized by the abundance of green color minerals. For example, chlorite, epidote, actinolite, chloritoid occur in peltic schist that are richer in FeO and Al2O3 and poorer in K2O. Other diagnostic minerals are mica, muscovite and biotite, microcline, pyrophyllite, kyanite and garnet, etc. Subfacies and zones of greenschist facies. Mineralogical changes in peltic schist as the classic chlorite, biotite and almandine garnet are isogrades of barope are used to divide the greenschist facies into 3 subzones or subfacies or zones. Zone/subfacies: chlorite zone, quartz, albite, muscovite, chlorite subfaces; biotite zone, quartz, albite, epidote, biotite subfaces; almandine zone, quartz, albite, epidote, almandine subfaces. Figure AFM diagram of chloride zone. The peltic assemblages are first chlorite, pyrophyllite, muscovite, fensite variety plus quartz, albite epidote plus minus paragonite. Second, chlorite, chloritoid, muscovite, quartz, albite epidote plus minus paragonite. Third, chlorite, chloritoid, pyrophyllite with quartz, albite epidote plus minus paragonite. Fourth, chlorite, muscovite with quartz, albite epidote paragonite. Biotite zone. The beginning of biotite zone is indicated by the appearance of biotite by the following reaction: muscovite plus chlorite give rise to biotite plus Al rich chloride plus quartz plus water, reaction number 3. Another reaction is microcline plus chlorite give rise to biotite plus muscovite plus quartz, reaction number 4. By the reaction 3 and 4, chloride become unstable in presence of microcline. Furthermore, steplomelans is unstable in this reaction as it reacts with muscovite to form biotite and chlorite. By the reaction, steplomelan plus muscovite give rise to biotite plus chloride plus quartz. This reaction was carried out by Nice 1970, 445 degree centigrade 4 kilobar, 460 degree centigrade 7 kilobar. In aluminous peltic rocks, kyanite appear in place of pyrophyllite. By the reaction, pyrophyllite give rise to kyanite plus SiO2 plus water, reaction number 5. This reaction was carried out by Carrick 1968, 430 degree centigrade 3.9 kilobar, 400 degree centigrade 1 kilobar. Mineral assemblages, mineral paragenesis. On the basis of AFM, we can observe the formation of two new minerals, the first appearance of biotite and kyanite during biotite zone of green facies. Peltic rocks, assemblages 1 to 4, same as chloride zone except the occurrences of kyanite instead of pyrophyllite in assemblages. Number 1, kyanite, chlorite, muscovite with quartz, albite epidote. Number 2, chloritoid, chlorite, muscovite with quartz, albite epidote. Number 3, kyanite, chlorite, chloritoid with quartz, albite epidote. Number 4, muscovite plus chlorite along with quartz, albite plus minus epidote. Number 5, biotite, muscovite, chlorite with quartz, albite plus minus epidote. Almandine zone. The first appearance of almandine is indicated by the beginning of the almandine zone of green facies. FeMg chlorite plus quartz give rise to almandine plus Mg chloride plus water, reaction number 6. Another reaction is Fe rich chlorite plus muscovite plus quartz give rise to almandine plus biotite plus minus kyanite plus water. Mineral assemblages or paragenesis. On the basis of AFM diagram, we can recognize the following assemblages. Peltic rocks. Number 1, kyanite, chloritoid, chlorite along with quartz, albite plus minus epidote. Number 2, kyanite, chlorite, muscovite with quartz, albite plus minus epidote. Number 3, kyanite, chloritoid, chlorite with quartz, muscovite, albite plus minus epidote. Number 4, biotite, chlorite, muscovite with quartz, albite plus minus epidote. Number 5, almandine, biotite, chlorite with muscovite, quartz, albite plus minus epidote. Today in this lecture, we have discussed about the regional metamorphism of peltic rocks, part 2. We have covered this topic under the following heads: chloride zone, biotite zone and almandine zone. I believe this lecture was useful for you. In my next lecture, I will cover stolite zone, kyanite almandine zone, sillimanite muscovite zone and sillimanite orthoclase zone. For further studies, please read the textbook, references and links given in the text.